Okay, so as we calculate intensity with spherical waves with a certain distance, we can do that as well. And we do that by taking the power and we divide that by the surface area of a sphere, which is 4 pi r squared. And that should make sense because as sound travels out, it travels out spherically, and that power is being spread out over the surface area of a sphere itself. And so we can get, whatever that intensity is. So we take that power divided by the 4 pi, and then r is the distance from the source, and power is in watts. And so we end up getting for intensity a watt per meter squared. This E over T represents energy in a period of time. That's just, how much energy is pumped in out of a sound source in a period of time. So let's take a look at this example here. Let's compare what the intensity sounds like at 3 meters versus 6 meters. So if you're 3 meters away versus if you're 6 meters away, we have a 200 watt speaker. So what I'm going to have you do is go ahead and calculate the intensity at 3 meters, and you can calculate the intensity at 6 meters, and then compare the two. How does one compare to the other? So go ahead and pause the clip and calculate those and compare them. And then when you're ready to check, you can hit play to continue. Okay, so for 3 meters, you should get 1.768 watts per meter squared for the intensity. For the 6 meters, you should get 0.442. So if we take the new over the old, 4 over 1, so it's actually 4 times more intense right here. 4 times more intense. We doubled the radius, right? So the radius is double. So we would think, oh, maybe this would be half here, or that maybe this would be double than this one. But it turns out it's actually, it decreases very rapidly as you get further and further out. That's because the sound source is spreading out spherically, and as it spreads out spherically, the intensity is spread out over that whole sphere, and it's an inverse squared relationship. Let's say you're at a concert and let's say you have speakers that are 9,000 watts and you are a certain distance from the stage, and let's say that you're picking up an intensity of 1.146 watt per meter squared. Go ahead and figure out how far you are from the stage. So go ahead and pause the clip and give this a try, and then when you're ready to check, you can hit play to continue. Okay, so you should get a radius of 25 meters, so that's how far away you would be from the stage. So pretty close to the scale here, if you're standing this tall, yeah, it'd be pretty close to 25 meters if that's what it would look like, that maybe a little bit further out. Now the ear is really cool because we have different parts of our ear, and the way the ear works is really, really beneficial for us as well. And so we have the outer ear where the sound travels down the ear canal to the eardrum. We have the middle ear with a hammer, anvil, and stirrup, and then that transfers the vibrations to the inner ear. Then the inner ear has the cochlea, and then it actually sends electrical signals eventually to the brain to perceive it. Now you don't need to memorize the different parts of the ear, but it's cool because this actually connects with resonance. What actually happens in the inner ear here is eventually, let's say you had a tuning fork that was 440 hertz, and you hit it, and the tuning fork's vibrating back and forth. Now your eardrum is going to vibrate back and forth at 440, right? And then it's going to go through your middle ear and eventually to your inner ear where the fluid's going to move at 440. Now it turns out that there's little hairs in there that resonate with 440, and that don't resonate with others. So as it goes through, only these hairs are going to resonate, and as they resonate, they'll send electrical signals to the brain, and then your brain will say, oh, 440. Well, it'll perceive that pitch, right? It won't know 440, but you'll perceive 440 as you hear it. This picture represents sound in, or actually intensity and frequency for a human ear. And in class, I have us analyze this for a while. This shaded region represents what we can hear. And so the threshold of hearing represents the area where, that's the minimum intensity needed per frequency that we can actually hear. So if you notice with the higher frequencies here, 2,000, 5,000, you actually don't need much sound. This is like that high pitch you could hear, coming from a old TV, or, just a high pitch from an appliance or something like that would be around this. It doesn't take much noise. But if you're around this range, let's say like a bass speaker, you need more intensity for sure to be able to even just hear it. Now, the threshold of pain, we reach that earlier, right, with these higher pitches. And so if you've ever been close to have a microphone that accidentally gets placed next to a speaker and you get that loud screech, you're reaching the threshold of pain very quickly because, you're at a high pitch, right? And, the intensity here is, around here. And so, yeah, you're going to reach the threshold of pain quicker than compared to a bass speaker, which you can handle more noise. The music region is greater than the speech region. We can have musical instruments that go to a higher frequency or a lower frequency than speech can. In music, you can have an instrument that's pumping out a lot of sound versus the speech, where maybe not so much. And, we can hear up until about 20,000 hertz. And then we can go down all the way to about 20 hertz, and that's our range there. Now, what's also cool about our ears is, let's say, we're at a concert, and let's say we're at maybe an orchestra concert, so we have, a lot of people on the stage here. Let's say you had, 80 musicians maybe, and you're sitting out here, you're enjoying the concert. And let's say you have a solo. So that solo is playing, you're enjoying it, everything's good. Then maybe 2 more people come and you're still good to go, right? But then 80 people start to play, right? Now, to you, it doesn't sound 80 times as loud, right? It still sounds good to you, but it's not 80 times as loud. And so what's cool about our ears as well is that it can handle a lot of intensity. And the loudness to us is not directly proportional to the intensity. If it was, we'd be in big trouble. We could be in crowds, if we're at the Super Bowl, right? And we're sitting there, and let's say, there's 80,000 people in the stadium, and at the Super Bowl, everybody's hyped, and someone gets a touchdown, 40,000 people are really happy, half the fans. And so everybody's screaming, and you have 40,000 times the intensity, right? You have, depending on the distance, but you've got a lot more sound, but you don't have to block your ears, right? So you can handle a lot of noise, or you can appreciate just one instrument or one person singing or whatever. And so that's significant because, with, for any concert or any time that you're listening to something, that's going to be significant. So here's a table of intensity versus decibel level. Decibel level is loudness. Intensity is the physical air being pushed. So if I start to whisper, right, and I do this in class, I'm starting to whisper. This is my watts per meter squared, and this is the decibel level. Everybody can still hear me even though I'm whispering. But let's say, you're standing and someone wants to mess with you, and they honk the car horn and you're right next to it, right? Now, it is a lot louder, right? So it's about 4 times as loud to you. But look at how much more air is being pumped. In this case, you have 0.1, 2, 3, 4, 5, 6, 7, 8 watts per meter squared. But with a car horn, 0.1. This is so much more than this, right? I mean, how many times more? Crazy amount, right? So you have a lot more air being pumped, but to you, it only sounds to you maybe 4 times as loud, which is pretty crazy, right? So our ears can handle a lot of noise. So in terms of intensity of sound with a decibel level, we're looking at a range, perceived loudness, and the perceived loudness again is not directly proportional. It's actually a logarithmic relationship. So here's another table of different ones. You got a loud rock concert as 1 watt per meter squared. That's 120 decibels versus whisper, but this is so much smaller, right? 10 zeros, and then versus, you got a lot of noise here. So a lot of times, and here's an example of some headsets that we use for aviation, and it rates this as reducing 23 decibels. So in our everyday life, we're dealing with decibel values, and so it's important to be able to go back and forth from intensity to decibel level, and that's what we're going to do here. So this logarithmic relationship is based on, we have beta here in decibels, that's loudness, and then I is intensity, and I0 is the threshold of hearing. So I0 is a constant that we have in there. I is the actual intensity of whatever sound source we have, and then B is the scale that we have. So let's take a look at this example. We'll start with this one here. Let's say we have a jet engine, or just an aircraft engine, that has an intensity of 0.11 watts per meter squared, and it hits your headset. So if your headset gives you 24 decibels of noise reduction, what decibel level will you actually hear at your ear? So why don't you go ahead and try that using the equation that you just wrote down, and give that a shot. So go ahead and pause the clip and give this a try. Then when you're ready to check, you can hit play to continue. Okay, so you're inside the airplane, and you have your decibel level here, 10 log 0.11 over 1 times 10 to the negative 12th. So 110 decibels is what you would have at your ear, but you have 24 decibel noise reduction, so we can subtract that out. So this is actually what will reach your ear, 86.41 decibels. And that makes a big difference when you're flying, because the headset themselves, reduce it enough to make it more comfortable. So 86 can be comfortable.